Okay, some additional rules today. First of all, the general rule is here. So we've already developed this rule. If f of x equals axn, a is just a number, the coefficient, x to the power of something. We bring that power down to the front as a multiplier, and then we reduce the power by 1. And that will give us our gradient function. So that's differentiation of a polynomial. Basically, that's the rule. And we've got that rule there, and it's also in that orange cloud above. And now I've written in purple just a verbal version of that rule. 1, 2, and 3 are additional rules. 2 of them we've already talked about. So rule number 1 is if you have a function that's just a constant. If it's just a number, when you derive that function, you get 0. And we talked about why last lesson. So it's all to do with the fact that that constant is actually cx to the power of 0. When you bring the 0 out the front, the whole thing disappears. So when you derive a constant, it vanishes. It doesn't really disappear, it turns into 0, so it's still there, it's just 0. 2, if f of x is some linear term. So I'm going to start talking about the linear term, the constant term, the cubic term, which will be something x cubed. I'll be referring to specific terms within the polynomial. If it's a linear term, when you derive it, it just becomes the coefficient. So 7x derives to give 7, and 10x derives to give 10, and 30x derives to give 30, and negative 3x derives to give negative 3. And I'll bring those 2 rules up because they seem a bit trivial, but they're actually the ones people get wrong more often than cubics and quartics, etc. Because they kind of don't follow that rule the way you expect them to in some ways. So you've got to be a bit careful with these. The last rule, which we haven't spoken about, is if you have a polynomial that has separate terms, we derive each term individually. You don't have to worry about mixing them up. Okay? So in this case, if I've got a polynomial that has 3x cubed plus 2x squared, I just derive 3x cubed as if it's by itself, and then I derive 2x squared as if it's by itself. And that's all I need to do. So you're just going to treat separate terms separately. A new term is something that's separated by a plus or minus. Then it's a new term. So some further examples. I've got example 2, and example 3, and example 4, and then I'll leave it alone. And they won't take too long. So example 2, determine the derivative in each case. So for part A, I need to derive f of x. Remember our derivative notation, if it's giving you a function f of x, typically we'll derive by saying, pen stopped on me, that pen's not working, f dash of x. So that'll be how we notate our derivative. And our derivative in this case is 2 times 3x to the power of 2 minus 1. I've really built that out the longest way possible. If you can work out 2 minus 1 in your head, great, put it on there, I don't really care. Plus, 2x is a linear term, it just goes to 2, and then minus 3 derives to 0, and so I get 6x to the power of 1, which is just 6x plus 2. I've treated every single term separately. That's term 1. That goes to there, that's term 2, and term 3 is a constant, so it becomes 0, and I'll just leave it alone. Any questions on that one? B, now there's going to be a shorter way of doing B, and maybe some of you have explored this already, but I'm going to tell you that in this case, we don't have a shorter way. So I'm doing this example to lead into our chain rule work later this week. But with B, we don't know how to do it except to expand the brackets. So if you see a question like this with a low power, you can expand the brackets, that will work. So y is equal to 2x minus 1 times 2x minus 1, which if you do that, you'll get 4x squared minus 4x plus 1. And y dash, which is one way of writing it, or dy dx, which is the other way of writing it, is equal to 8x to the power of 1, so just 8x. The 2 came out the front, 2 times 4 is 8, minus 4. And the 1 just becomes 0. So that's that derivative. I just had to expand first. Okay? And question C looks a bit trickier. This could be done with something called the quotient rule, which we will get to in the next week or so. But for now, there's something special about question C, and that is that it can be simplified. So I can write this down as 2x to the power of 5 over x cubed minus x over x cubed. And that becomes 2x squared minus x to the power of negative 2. So this example also brings out the negative indices example as well, which I'm hoping that I can give myself a couple of lines of extra space here. When I derive that, so to determine dy dx, I get 4x, the 2 comes out the front, multiplies by 2x to the power of 1. But here I get negative, and I bring the power out the front, negative 2 times x to the power of negative 2 minus 1. So you have to be a little bit careful here. I've put the negative 2 at the front, and I've reduced the power by 1, which actually makes it negative 3. And a lot of people might write negative 1, which would be wrong. So I get 4x plus 2x to the power of negative 3. And because the question was given to me as a fraction, I'll write my answer as a fraction as well. So it's 4x plus 2 over x cubed. So that's a bit trickier, but I've done the rule. Don't forget, we just do the rule. Don't assume anything, just follow the rule. The rule is negative 2 comes out the front and reduces by 1 in the power. Done. As long as I do that, I'll get it right every time. Any questions on that one? Example 3 is basically the same, just with a little bit of an extension thing that you need to be aware of. The question's asking me to find f dash of 3, which verbally is, I want you to find the gradient at x equals 3. Because remember, f dash is our gradient function. So the first thing we're going to do is find f dash of x. And again, this is 5 comes out the front, 5 times 7 is 35. X to the power of 4, because 5 minus 1 is 4. Minus 4 times 10 is 40. X to the power of 3, because 4 minus 1 is 3. Plus 7, and the minus 17 disappears, it becomes 0. Okay, so again, I've just done each individually. And that means that f dash of 3 is equal to 35 times 3 to the power of 4 minus 40 times 3 cubed plus 7. 35 times 3 to the power of 4. This got out of hand, I didn't mean it to be this big. 3 cubed plus 7 is a gradient of 1,762. So that's rather steep. Yeah? Cool. Any questions on that one? Process is pretty straightforward. And the last question, and this is also common. This is how we make this exercise hard. And it's not really that bad. So we're given a function y equals x to the power of 7 plus bx to the power of 4 minus 3x plus 7. So this b is our problem. But we're told that the gradient is 0 at x equals 1. So I'm going to go through and go, well, if I substitute 1 into the gradient function, it's equal to 0, and then I'll be able to solve that for b. So let's find the gradient function first. Dy dx is equal to x to the power of 7 becomes 7x to the power of 6. Bx to the power of 4 becomes 4bx cubed minus 3. And at x equals 1, dy dx equals 0. So I get 0 is equal to 7 times 1 to the power of 6 plus 4b times 1 cubed minus 3. And that gives me 7 plus 4b minus 3 is equal to 0. And 7 minus 3 is 4. Subtract 4 from both sides, I get negative 4 equals 4b, and therefore b must equal negative 1. Question done. They're about as hard as they're going to get at the moment. Don't get me wrong, calculus does get tricky at times, but right now you're just practicing that differentiation skill, and that's about as hard as they're going to get. And that's it. I'm going to leave it there. I'll just stop this.